Hello, I'm Jeff Kane, an Associate Professor of Fire Ecology and Fuels Management at Humboldt State University. I'd like to share some information regarding considerations for prescribed burning in mechanically masticated fuel beds. This project was funded through a USDA Western Sustainable Agriculture Research and Education Project and coordinated by the University of California Cooperative Extension. In this presentation, I will cover mechanical mastication and the characteristics of masticated fuel beds, the benefits and drawbacks of prescribed burning in masticated fuel beds, and some operational considerations to meet management objectives. Mastication is a type of mechanical fuel treatment that typically treats shrubs and small trees, reducing mid-story fuel heights and retaining all debris on site. There are many different types of equipment that are used for mechanical mastication, but the cutting heads are typically in two broad categories, either a rotary drum with flailing knives or a large, typically circular blade, and these heads can be mounted on the boom of an excavator or on the front end of a small bobcat-style vehicle. Mechanical mastication results in fuel beds that are largely composed of fine woody fuels less than 1 inch in diameter, or within the 1 and 10-hour time lag classes. However, some sites may have a higher proportion of fuels in the 100-hour time lag class. Somewhat subtle differences in the proportion of fuel loading by size class will likely depend on the vegetation type, mastication equipment being used, and the style and experience of equipment operators. Based on a study of masticated fuel beds of Northern California and Southern Oregon, fine fuel loading values ranged between 4 and 30 tons per acre and had fuel bed depths of less than 1 foot, resulting in a highly compacted fuel bed composed of mostly woody materials. It is these characteristics that distinguish masticated fuel beds from other fuel types, as demonstrated on the figure to the right. Mastication treatments can increase the feasibility of prescribed fire. The translocation of shrubs and small trees to a more compacted fuel bed makes it much easier for practitioners to navigate through and ignite units. It may also reduce the potential for torching or crowning if the crown base height is sufficiently increased in forested stands. Another benefit of prescribed burning in masticated fuels is that in most cases, fire behavior will be low to moderate. For instance, spring prescribed burns conducted in masticated stands of Northern California, when fuel moistures were between 10 and 20% and wind speeds were less than 2 miles per hour, resulted in a head fire with flame lengths between 2 and 3 feet and a rate of spread of roughly 1 to 4 chains per hour. Backing fires had flame lengths of 1 to 2 feet with rate of spread between 0.2 and 0.3 chains per hour. Percent consumption of dead woody fuels in masticated sites ranged between 30 and 98%, with smaller fuels resulting in more consumption. Treatments that include a combination of mastication and prescribed burning that result in an increased canopy base height and substantial fuel reduction will likely promote greater resistance during wildfire. Mastication treatments followed by prescribed fire can also effectively increase understory plant cover and diversity. In a study conducted in Northern California, mastication and prescribed burning treatments increased cover by 200% and species richness by 150% compared to untreated areas. Increases in understory vegetation is primarily associated with increased light availability and greater exposure of bare mineral soil. However, there are some potential drawbacks to prescribed burning in masticated areas. The high fuel loads and compact nature of the fuel beds can result in prolonged residence time and higher fire line intensity. Here we see that in the laboratory experiment, increases in fuel loading from 11 to 33 tons per acre resulted in an increase in fire line intensity and duration of burning across masticated fuels ranging in age between 2 and 16 years. Additionally, the compact nature of these fuels may also promote greater smoldering and potentially greater smoke production. Prolonged smoldering could also compromise control lines during prescribed burns. The substantial fire line intensity in masticated sites may also contribute to increased tree mortality resulting from burning due to either ground scorch or cambial heating. Based on a study of two different masticated sites in Northern California, tree mortality was relatively low at 7 and 34%. Smaller trees with greater ground scorch had a higher probability of mortality. The site with higher tree mortality also had steeper slopes and higher fuel loads. Experimental treatments that raked masticated fuels away from tree boles did not effectively reduce tree mortality. Thus, crown scorch is likely the larger contributor to tree mortality following prescribed burning in masticated sites. Increased fire line intensities may also contribute to extended soil heating above the lethal threshold, typically 140 degrees Fahrenheit for 1 minute, that can result in the death of most living tissues in the soil, such as roots, seeds, and fungi. Areas with high fuel loads that burn during low fuel moisture conditions will likely result in the highest temperatures, longest lethal durations, and heat that can penetrate deeper into the soil profile. Areas with lower load and higher moisture conditions can ameliorate this effect. A potentially undesired outcome of prescribed burning in masticated fuel beds is that the germination of shrub seeds in the soil seed bank may be stimulated. Following a spring burn in masticated fuel beds, the density of shrub stems increased by 5 times compared to mastication only. Managers interested in reducing shrub density and increasing the longevity of treatments may not prefer to conduct a prescribed burn following mastication. Prescribed fire in masticated stands may also increase non-native species density. Here we see an example of where mastication followed by prescribed burning increased the density of non-native forbs such as bull thistle compared to untreated areas. However, mastication treatments alone had slightly higher densities. Managers interested in more accurately predicting prescribed fire behavior in masticated fuel beds would likely require the use of custom fuel models. There are currently 3 custom fuel models for masticated sites, based on experimental prescribed burns in Northern California that cover low, moderate, and high fuel loading conditions. Generally speaking, masticated fuel beds tend to burn slower with higher flame lengths compared to some existing timber litter and slash models that might be used. In the figure to the left, we can see that as the depth and load of masticated sites increases, predicted rate of spread and flame length generally decreases. However, based on predicted fire line intensities from these custom models, the amount of crown scorch is underpredicted by a factor of about 1.8. Thus, a stand with a predicted scorch height of 10 feet would have an observed scorch height around 18 feet. Burn objectives. Managers may need to consider modifying ignition patterns and the timing of burns. For instance, if objectives require greater consumption and less smoke production, utilizing backing burns during dry conditions may be desired. However, this may result in more soil heating in areas with higher fuel loads. To burn higher fuel load sites, managers may consider burning in the spring or at nighttime when fuel moisture conditions are higher to limit the potential negative impacts from soil heating. To summarize, mechanical mastication can create a unique fuel bed characterized by a dense layer of mostly fine woody fuels. Benefits to prescribed burning in masticated fuels include increased navigability through units, low to moderate fire behavior, generally good fuel consumption, and the combination of mastication and prescribed fire will likely effectively reduce wildfire impacts. It can also be used to increase the understory vegetation cover and diversity. However, there are also some potential drawbacks to prescribed burning in masticated fuels. These include increased soil heating, non-native species, and stimulation of shrub germination. Yet, some of these drawbacks can be mitigated by altering the prescription, ignition patterns, and timing of burning. Citations of research studies presented here are provided with some additional resources related to the topic. Thank you for listening to this presentation. I hope you have found this information helpful. Please feel free to contact me if you have any questions about prescribed burning and masticated fuel beds.